Welcome student of Calculus 3 to this example where we need to verify the divergence theorem for this vector field where E is a very clear solid. It's the solid bounded by the paraboloid x squared plus y squared and the plane z equal to 9. So in order to verify the divergence theorem, we need to calculate the triple integral of the divergence over this region, and we need to calculate the flux FDS for this. So this video will be having a continuation in part 2 where we need to find the flux. So first I will find the triple integral for the divergence, and in order to do that, the first step is we need to find what is the divergence. So divergence of f, which is we take the derivative of the first component with respect to x, and that is 0. Derivative of the second component with respect to y, and that is 2z. And finally, the component with respect to z, which is 8z. So the answer is 10z. So we need to find the triple integral of 10z dv. And in order to do that, we need to sketch the region and we try to find at least a bound for the z. Now, if we sketch the region, it's a paraboloid going upward. So we have it like this. And then we have intersection with the plane z equal to 9. So we stop at 9. Now, if we look at the bounds for z, it's starting the bottom at this function here, and at the top we reach the plane z equal to 9. So the z will be between 9 and the paraboloid, which is x squared plus y squared. So this here integral here will be double integral over a region between x and y, and then we have the third integral, which starts with x squared plus y squared, end up at 9 for the 10z dz, and then we have dA. Now let's evaluate this integral here. So the one in white will wait until we finish. The one in green, it will be 10z squared over 2, so I can just write it 5z. And then the integral from x squared plus y squared to 9. And now this integral here is 405 minus 5 x squared plus y squared dA. So this is my integral that I need to find the double integral. Now, in order to double integral, I need to see what's happening here, down here between x and y. Of course, if we look at the projection of the whole surface into xy plane, what we will see is just a circle with radius 3, because we have 9 here. So if we just get everything down here and see what's x and y, if we smash it here, it will be a circle of radius 3. And therefore, that circle, we will just use the polar coordinate. So if we just go and do the polar coordinate, it will be from 0 to 2 pi, integral from 0 to 3, and then we have 405 minus 5. This will become r squared, because d squared z squared is r squared. And then we have here r dr d theta. So to be 0 to 2 pi, integral from 0 to 3. Here we'll get 405r minus 5r cubed dr d theta. We just go ahead and we find the integral of this. So it would be 405 r squared over 2 minus 5 over 4 r4. We substitute it from 0 to 3 d theta, which would be, if we find everything correctly, this would be 360 over 2 minus 405 . $225 d theta. So the final answer will be 4050 pi. And that's what we get here. If all the calculation is correct, this is what we should get. Now, what we will do in part 2, we will find the flux. And how we find the flux, we will use the evaluation of surface integral to find the flux, and hopefully we get the same answer